Okay, perfect. Yeah, seems to work. Thank you so much. Hi, I'm Timo and working at Element. And I have the great honor to give you the first little bit of technical introduction to Matrix RTC, something we've worked on for like quite a bit now. And it's like quite a complex topic because it's introducing something fairly new to Matrix. And I called the talk the Not Anymore Missing Piece to Enable Great Video Conferences. The reason for the not anymore is that the proposals are finally in a state where they more or less converge. And the initial implementations are becoming stable. So I'm mostly talking here about Element Call, which, yeah, we already have a demo in the Element X launch presentation, and Florian Hees has given a dedicated Element Call presentation. So I'm actually super excited about this talk because it's right at the time with this conference where things are mostly stable, at least the core Matrix RTC bits. And yeah, that basically makes this the first introductory documentation for Matrix RTC, because we have been only doing R&D and figuring things out, and there was like very little time for documentation, which is always a bummer. Will change, but that's the first bit of it. Okay, so I wrote there, the Matrix RTC approach checks more boxes for VoIP than ever before. So there have been multiple VoIP implementations, but with the basis of Matrix RTC, we finally are at the point where we have scalability, interchangeable components, which is something that is super core to native. If we think about crypto, there we also have like a system to change the version of crypto and even the implementation. And we try to also bring this to VoIP, because there's like, yeah, an even higher demand for like replacing whole pieces for it if there's something new emerging. It's super flexible. So it's not called RTC video calling, it's called Matrix RTC without video or audio in there, because there is lots of other things you can do. You can, yeah, build things like Third Room on it, or Work Adventure, or anything that is real time. And of course, it's secure, federated, has verified identities, so the whole security bits from Matrix can just be leveraged. And yeah, like the properties there are like super, super amazing. And here again, as I said before, this is basically the first time we can give some introduction and some documentation about all this in its mostly final state. So I show this figure in the beginning. I use it in a bunch of variations during the talk, so just we have a really good understanding of it. I'm trying to display a federated matrix room with it. So we have home server A, home server B, a room in this home server, and of course, like the two core components of a room, it's state events and room events. State events I'm showing here, room events there. So pretty basic, but yeah, we'll reuse this to then, yeah, go through the agenda for the components we'll discuss today. So first of all, we have our WebRTC infrastructure. That is what is actually doing the RTC streams. So in the main case, which is currently as I said, it's like you can exchange components, but currently it's LiveKit. And I think it will be LiveKit for quite a long time because it's a pretty decent project. And that is the WebRTC infrastructure, which we have at the top there. So each home server is supposed to have a LiveKit SFU in the future, can be thought of as a replacement for the turn servers. So currently, if you want to have calling, you already have such an add-on component to each home server, which is a turn server. And LiveKit basically can just replace this bit. And it's like, if it's not used a lot, it's a quite lightweight addition. Then we have the signaling. And that is 2 bits, basically, like the high-level signaling. One is exchanging the backend information. I showed this with like an extension of the room state, which decides which LiveKit server actually to use. And then, of course, the call state is also responsible to just communicate who is in the call in the current room. The next, like this is the second really big chunk of Matrix RTC, or the next component. The third one is the metadata. So basically, independent of how we do our RTC streams, we can still use Matrix, and we can also specify how Matrix is used to extend the whatever Matrix RTC session you have, be it live work adventure or a video call, with additional things. And like examples would be, how do we store the call history? How do we do ringing? And then the last bit, encryption. That's of course also a core piece. How do we exchange keys? How do we find a shared or like per sender secret for this one RTC session. And we use 2 device messages for this. And I indicated this in this picture with this line. And of course, this might be very annoying for a couple of people here, because of course, 2 device messages still go through the home server, but there are like so many lines in here anyways. So I simplified it. So 2 device actually is a line from one device to the other, which is not technically correct. Cool. So we start with our first chapter. We talk about room state and how the room state in MatrixRTC is used for the high-level signaling. So here we have the full picture. So that's the section we talk about now. Okay, so here with this next couple of slides, I kind of give you a little insight in how it is to think about those problems. So this is not how it's done, but we'll still go through it and think about what kind of problems you have to give you a chance to also be part of the fun to design such a thing. So we have the intuitive approach, which is just let's do a call. Let's do a call event for this call. That's it. Super clear. A call is a state event, and it says which infrastructure to use and everything. But with this, we run into issues. So one is, if there's a confused, broken, or malicious client, they of course also have to have the option to interact with this call. So they could just update it, say, I want this call to be on a different SFU, a different backend. They can just change it. And what will happen is that now, if that's a broken backend, the call is broken for everyone. One broken malicious client can break it for everyone. And that's something we really don't want to have. Now you could argue, okay, but if somebody's changing the state, why don't the others just stick to the old state, which it was before, and just continue to use the old LiveKit SFU, which was working? And the issue there is that for future clients, you then run into split brains. So here's an example. First client propagates one SFU. Second client joins. This client is confused, updates the call member, the one big call event. And now the third client checks the event and joins this confused client. So now they are in a different room than this one. So we kind of don't really have the choice to not listen to changes to this. But if we listen to changes, we're in the situation before again, where people can override it and break the whole experience. So the solution for this is only use call member events. So we simplified the whole thing from one call event to an array of memberships to just have call member events. That's it. So it actually becomes quite simple from that point of view. And you still want to have one shared instance where you converge to what SFU to use and those parameters which are shared. And this is very similar to what we do with state resolution. So basically, there's this virtual combined event, which doesn't really exist in the DAG, but everybody has the same algorithm to compute this combined piece of data to then, have the same information to build the call on. And if this always converges, and if all our algorithms are designed in a way that we end up with the same virtual call event on each client, we're good. And it always should be one call for everyone. And then we go through the disaster scenario again. One confused client is updating their call member event, but the algorithm which generates the shared overall call description would still stick to one specific, or the most important thing, it would be the same on all clients. So maybe this one is still confused because broken, but the others still have a decent experience, which is the important bit. So MatrixRTC is now only a collection of members, basically nothing else, at least this state part of MatrixRTC. So every room can always be used as a MatrixRTC session, just put member state events in there. And everything else would then be application specific. So we are currently not talking really about calls. We are talking about, even though it's called call member, that's something that is still in discussion, but we are talking about just RTC sessions, can be anything. And they only have this one bit to it. So old was member event and members, or sorry, call event and members, and now it's just a collection of member events, and there can still be multiple sessions. The member events just say, I want to be in this session, and the other says, I want to be in that session. So since it's now only this one bit of information, this one call member event, it's time to look deeper into what this event actually looks like. And here I have a full JSON for this call member event. but it's not too complicated. So we can separate it out in what's the core matrix RTC bits. That's what state key you use ID plus device ID. What application it is, that's quite important, because as I said, there can be multiple applications. They can evolve, there can be a new one. In this case, it's just an mcall. And then we have the infrastructure bit. That's also a clear defined set of informations to then find what infrastructure this call is based on. Is it LiveKit, is it full mesh, or something new we haven't yet found out about. So here again, Matrix RTC, the overall box, everything in black, infrastructure, the blue bits, and then the application-specific fields. And yeah, as I said before, there can be multiple applications, multiple implementations. So now let's talk about the actual core bit of finding the focus selection. Wait, does this mean in 5 minutes the talk is over? Oh. It should be a 45-minute talk. I was quite surprised because okay, cool. I thought the first time was like, there's 10 minutes left. Sorry for the interruption. So we are like deep in the, maybe it's not too bad. So we are deep in the core piece of finding what infrastructure to use based on the room state. We just discussed the whole JSON event, and now we talk about the blue section. So focus active, and foci preferred. And they kind of have a verbal meaning. Foci active can be translated as the algorithm that defines how to choose a focus for this member. And the foci preferred is the input data for this algorithm contributed by this member. So we end up in a world where everybody who joins can give a list of inputs. And then everybody says how, based on those inputs, they are reachable. And that is, of course, tricky. Like, you can't put any logic in here, but the logic which ends up in the spec hopefully is designed in a way so it actually always converges. So the foci preferred, where do they come from? The most important, as I said, each home server has an SFU attached. So there the logic is that the well-known is advocating one SFU, and then each user is supposed to put the first SFU from the well-known from their home server into this array. And then there can be additional fields. For instance, right now, will be changed. Element is actually putting their own SFU into each client. So right now, I think still today, you could also use it without an SFU, and you would just fall back and using the donated element SFU, but this will change. So in the future, everybody needs to have a home server which advocates an SFU, just so we have a basically stopgap solution where people didn't really had any time to host an SFU. We added this element donated one. Yeah, that's it. What did I say here? The focus active needs to be designed. Yeah, sure. Otherwise, if that's a bad algorithm, it wouldn't work. So we just talked about the whole LiveKit, but there is a path with this setup to have full mesh back. And it would be super simple. We just say the focus active type is full mesh. Everybody joins with focus active type full mesh. And then there's it is basically then defining the algorithm that you have to build up a full mesh. Totally compatible with Matrix RTC. It just would need a spec for the full mesh focus active type. It would be that simple. And one could even think further. One could say, why not have another focus active type, which is full mesh into LiveKit? It would then still include LiveKit SFUs in the foci preferred array. And it would start at full mesh, and then there's a defined value until full mesh scales, maybe 5 is appropriate, I don't know, all up for spec discussions, and then it would transition into LiveKit. So that's also something one could think of, and then have a solution where you first start in full mesh, don't occupy any SFU. If you have a larger call, you can transition. So this is like a super flexible and simple system. So now, reliable state membership. That is something we have had lots of trouble with. So if you currently use Matrix RTC, you join, you create state memberships, but then at some point, people fail to clear up their state membership, and you'll get a wrong room state. And we go a little bit through detail here. So yeah, we have our old schema. I hope you all still remember it. I mean, it's quite simple. And then we have a client, and that client wants to join. So they take a state event, which is a join call state event, so basically a membership with a active membership, and they send it to the home server. the home server inserts into the room state, and now we have a connected mcall member event for this device. But now what happens is that for some reason this connection is cut accidentally. So network issue or some user pressing Control W or batteries out, like devices out of battery. And in this case, the client loses connection. Like those are the things I just listed, and the call will never end because it's just data in the room state, and there's no reason why it should change. And there's now a solution for this, and we call this. Let me just, yeah, perfect. And we call this delayed events. So basically, instead of just sending one event, so this is a new spec which we developed in context of MatrixRTC, and it's a quite cool addition to Matrix in general, not just MatrixRTC. And what you can do here is you send two events, one for joining, one for leaving, and the join event will immediately be in the DAG, but the leave event will be like hold in the home server A, and it will be hold in the home server A as long as there's a heartbeat from the Element web application. As soon as this heartbeat dies because of a lost connection, then it will be put into the DAG. Oh, okay. I was confused that there are slides missing, but yeah, that was just, okay, so now you basically already know how it works. We go a little bit more into detail. So I just introduced this new event type. And here is how this event type, or how this, it's not an event type, it's like more like a event sending mechanism. And here's how this actually looks like. So before you had the normal put event, but now you can add a question mark delay at the end. And that means you send the event, but the event isn't immediately put into the DAG. It stays on the home server for, in this case, 5,000 milliseconds, and then it will be put into the DAG. So this event, the leave reason lost connection, will not be immediately sent, but after 5 seconds. And the cool thing now is that if you send such an event, you get a delay ID from the home server, and you can use a new endpoint to restart this endpoint. So basically the 5-second scheduling could be restarted multiple times, and then the event isn't sent in 5 seconds, but in 10, 15, 20, 40 seconds, until the client stops sending this refresh. And that's basically a normal heartbeat mechanism. So now we go through the same procedure I tried to explain with the previous graphic. So we first send the leave call event, and then we lose connection, and the leave call event is cached on the home server. Since we lose connection, we cannot send the heartbeat anymore, so the 5-second timeout is happening. And then as soon as the 5-second timeout is happening, this event, which is not yet in the DAG, will be moved into the DAG, and we'll end up in a clean state where the call member is disconnected. And yeah, we of course also have it in the timeline of the room. And that is super cool, because this of course allows what we are currently doing, making room state reliable, because we always use this heartbeat refresh. But this actually makes so much more things possible. You can have self-destructing messages where you send a redact and just put a timeout to the redact. There's some metadata privacy concerns, so I'm not sure if this is like the best version to do self-destructing messages, but it's one which would work today with the newest version of Synapse at least. Then you can just schedule events. I mean, that's a very simple thing to do, which is also kind of cool. Since we'll look into this later, since we do have an event now to let your phone ring, you could also create a teapot timer. You could even do things like temporary room permissions, where you set the room permission to something and then send a delayed event, which is reverting the room permissions. Like lots of other possibilities here. So now, since we already teased the ringing system, we talk about metadata. So that's the overall topic or the word I choose for everything that is not really MatrixRTC, not just the state events, but it's the general additional data around MatrixRTC for specific applications. So this is now call specific. And we start with call history. That's of course also something that is neat, that you see when there was a call, with how many people, for how long. And we don't even need any additional data for this, because if we look at the call events, we of course also have the previous content for state events. So it's very easy for clients to distinguish between join and leave events. A join event is previous content was empty. And now it has the fields I showed before for a call membership, and leave is the other way around. Here it can be both. Either the content is empty, then the client properly disconnected, or the content is leave reason lost connection, then the client didn't properly disconnect. Instead, we had the delayed event with a timeout, and it sent the lost connection event. And if we can distinguish between those two events, and we look at the basically timeline of a room using the origin server timestamp, we can see we can basically compute sections in the timeline where this member was online or connected to the call. So here somebody joined and left, here another person joined, thought here he left. And with this information, one could easily compute the full state of the call. And you have like lots of information here. You have basically the distribution, at which time, how many people there were, like the total time and the total number of members in the call. So it's quite a neat way to compute history without duplicating any data. Next piece of metadata, ringing. Super simple. We introduced a new event type, and that event type actually uses intentional mentions, because this is already solving so many room muting, and do you even have the right to ring some or to notify somebody? So for this room mention, ring the whole room, you already need specific rights in a matrix room, so it will even be detected. And then the only new field is the notify type, where you can either do a proper ring or just a notify. And currently it's configured that the client will only send a ring if it's a DM room, and it will send a notify if it's more than a DM, if it's a group. And then, of course, yeah, it's on the clients to support this event and then do the ringing. And that is also something really cool. There's just super recently a community contribution from Milton, and that is doing raise hands, and that's just another piece of metadata. So I'm just bringing in this example because it's really nice to see how you can combine matrix pieces and matrix RTC pieces, and then choose the right thing for whatever you try to achieve. And how raise hand is implemented is that we have the call member event, and then with a relation to the call member event, a new raise hand event is sent. And if you stop raising your hand, you just redirect that event again. And that's super nice, because even if you're somebody joining later into the room, with relations, you can just query all the relations for all call member events, and then you have the current raise hand state without needing to arbitrarily paginate back for the beginning of the call. So now, the last topic, encryption. How is encryption solved? So again, here we have our overall picture again, and we are talking about this piece at the bottom, which should be aligned through the clients. So what we already have in Matrix. So we have Megalm, we have device verification, and we have secure channels to all participants through Olm channel. And now the question is basically how to use those things the best way possible to enable encryption in Matrix RTC. Because what we had as a requirement is that we don't just take the whole room as a secure group for calling, but we wanted to make it possible that if you have a room with 100 people and there are 5 people in a call, only those 5 people can encrypt the streams. And before we go more into detail how the actual encryption is done and how we do the key exchanging, I think it makes sense to talk about how encryption in real-time streams is working in the first place. And one core principle of this is that you first exchange the keys ahead of time. So basically, if I know for the next 10 seconds, I want to use this key, I try to exchange it to everybody, or for the next minute. So that's basically step one. And with this step, we end up that we have blue, green, and purple client here, and they already have all the keys pre-cached, at least for the next couple of minutes. And then they start to stream data. So basically, this is the upstream, the big line, and the thin lines are the downstream. And now if we just look at the blue line, for example, we started with key 2, and we are currently using key 2, and everybody's also using key 2 to decrypt things. And now we switched to key 1, so we pre-shared key 1. The index is there's no order to it. I'm just using random numbers here. Now I'm switching to key 1, and each of those frame trailers or S-frames, they will have the key in front. It's just 1 byte, so you can have like, yeah, not that many keys or different indices, so you have to rotate them if you reach the end. And you'll just include the number here, and then as soon as this package actually reaches the receiver, they already have the key and they can immediately decode the stream. So this is how it works, that you can have encryption with like latency in the key sharing, but you still have a no interrupted video stream. And now if we think about forward secrecy and post-compromising secrecy, we have quite a bunch of situations where we have to rotate key. So this is, again, similar to the graph we had before with the joining and leaving. So each line is a member. Gray means they are connected to the call. And here we have those black lines. And at each black line, it makes sense. I even forgot this black line. That's also kind of reasonable to have a key update here, where you want to rotate your keys. Because transitioning from green to yellow, you have this person joining. And this person shouldn't have the keys for those historic streams, because maybe this person has access to the SFU, so they also could download the streams, but they shouldn't know what has been spoken back then. So we need to have a new key for this person to join. Then we need to have another new key when this person joins. And then when this person leaves, we have to have a new key. And when this person leaves, another new key. And that way, we can always make sure that nobody can read the history. And yeah, also, nobody can read the history and nobody can read what the others are talking about, even though they already left. So that's those two terms. And the simplest approach, of course, is just doing a full mesh key exchange. So for each line, we just send keys to everyone. That works. It's quite expensive, but it's still like an option. And the other option is that we do a shared key approach. So basically, on each line, we select one person, and that person is then deciding a new key and sending it to everyone. And there's also a hybrid world where we first start with a per sender key. So whenever somebody new joins, in this case, the person at the top, they share their new personal key with everyone. And then there's one person in the room which gets elected to share a new salt or like a new variation of that key. And then everybody's combining those two with a specified way to then also have a new key. And that reduces the traffic a little bit, because in full mesh, everybody had to generate a new key and send it to everyone. And here we only have one person generating a new key, sending it to everybody. Everybody else is replying with their key. And then we only have one salt for each change. Exactly. And the last option is that we could also say, for joins at least, for joins, we can make it so that we then just ratchet the key. So basically, if somebody's new coming into the room, we don't have to share. We only have to share the key with the new person, but everybody else is just ratcheting it one step. So there's like another small optimizations. So in summary, like there's numerous small optimizations. We would first start with just full mesh and then find what is the most reasonable way. And so I said it's like simple. We just elect somebody and they are like generating the new key. But I also wanted to point out that this brings other complexities, because how to select somebody, there could be anti-glaring algorithms similar to how we do the SFU selections. Worst case, we just use the oldest member. But then we again have this paradigm that we really don't want one individual to be able to break the call for everyone. So what if we selected somebody, but this person just doesn't send a new key? Then we would be kind of in a trap. And here indicated that there could be a basically cascading effect where first this person has the responsibility, and then there's like a 10-second time window. And if that person fails to do its duty in this 10-second time window, then we have the next one with the responsibility to send the keys. And then if that person also fails, we have the last one. But those concepts, they work. They are still complicated, because what do you do if you're here and this person already sent the keys, but now you're getting the keys from the oldest one, then you also need to have additional rules. Okay, in that case, you use the oldest possible keys, so it's tricky. So to sum up, encryption could use ratcheting. It could also maybe do a sub-megalom session. MLS would also be a very elegant way to have like one shared secret in a group of people. We want to start with the full mesh, but the cool thing here is that this is also something that could be exchanged. And we could first use this encryption system and later on this one. The core like minimal parameter we want to have is that we can have the secret subgroup in a larger room. Yeah. But the conditions are great because like whatever we do, we always can leverage the existing matrix trust and encryption system. That is something that is actually super unique because like lots of or some other video conferences also do encryption, but then they enforce you for like mostly each conference, or like probably you can also cache it to do verification and just compare strings, which is like quite rough for just one video call, where in Matrix we already have all the ecosystem with verified devices, and with invisible crypto, this all will, yeah, be used much more and much more elegant. And those things we already have. It's basically, this topic is just about how do we then actually exchange the keys. Cool. So we're almost at the end. I just want to give myself another minute to do the key takeaways. So we have the interchangeable RTC backends, which is something super, super cool. Because we can start with LiveKit, can add full mesh later on, and if there's like a cloud-first solution, which is so much better, we can add this as an MSC and are always on the like best working technology for the Matrix calls. Then we have Matrix does help a lot with encryption, even though it's still like a quite complicated thing to like do the most performant and most stable thing. But at least we have the trust model and the device verification, which we just. I think my microphone, oh, now it's working again, perfect. Should I just check? Okay, test, test, test. Oh, wonderful, cool. And then the next key takeaway, that supporting just Matrix RTC is super simple, because the only thing we need to do is basically parse the RTC member events in the room, and that's it. Then you already know, is there a session, what application type is that session, and who is in there. But of course, you still cannot participate in a session. So this, basically a client supporting Matrix RTC would be very simple. A client supporting the m.call application of Matrix RTC, that's a whole another like thing, because then you need to have the calling, the notify event for ringing, and yeah, all those kind of things. And then we try to make it very extensible, like the rest of Matrix. So new different Matrix RTC apps are part of the design. So if you don't want to have a call, but something else, it is all like designed in a way so it's super easy to have like m.call conference, which has more features, or m.third room, or m.spatial for like a spatial experience, or m. like probably not m. but just work adventure for a work adventure experience. Yeah, and since it's so simple, this allows Matrix RTC to be ready now, and then grow into the right direction organically, basically. Similar to what we do with other parts of Matrix, where we start with this, we start with LiveKit, but if we see we really have a way for a cascading SFU, which is custom built and fits very well into the DNA of Matrix, we can like organically grow it into this direction, but still have like really good calling now, which is super, super nice. And that's it. Thank you so much for listening.
Thank you very, very much, and we have time for a couple of questions.
Thank you for the presentation. I have a question about reconnections. In the LiveKit side, it will be handled in case of internet loss or connection loss. how about the matrix side, the heartbeat, if it's like it's still not received or it was received?
So the question is, or would it help if I just go through one example if we have a disconnecting client? Okay, perfect. So if we have a client and that client loses connection, then both things stop. So on the one hand, they of course don't stream anything to the LiveKit SFU anymore. And on the other hand, they don't send the heartbeat to the Matrix home server anymore because they lost connection. And then probably the first thing which will happen, because that's more like in the millisecond range, is that LiveKit doesn't receive a stream anymore, so you don't see the video feed of that person anymore. But then in approximately 5 seconds, the home server will see, oh, I lost connection to this user, so I send a hang-up event. And then the room state will converge, and everybody sees, oh, in the room state, there's also a missing user. And then it's basically like a proper clean hang-up. And since you bring up this question, there's actually another way to do this, which would be much more elegant than with the heartbeat. And that would be that we use scoped access tokens, which is something we don't have yet, but is something people think about and plan and want to have. And we could say for this one endpoint, like sending the leave event into the room, we have one dedicated access token, and then we could send this access token to the SFU. So you basically delegate the power to the SFU to send one specific event in your name. With cryptographic identities, this would be even more elegant, because then you can even like pre-sign the event, like it would also work. And then the SFU would be in control to see, oh, you disconnected, and then it would have the one right to send to the room state that you actually disconnect, and then we don't need the heartbeat to be that high frequency, not 5 seconds, but more like 7 hours maybe. But yeah, that's even a more promising solution. But even now, like this heartbeat is super low resources because there's no interaction with the database or the DAG. It's literally just one field updated that this event doesn't time out now, but like 5 seconds later.
In the ringing system, is there a way of explicitly declining an incoming call?
Not really. This is actually really, I mean, this is still part of the metadata, so it's not like this is entirely impossible, but it would require a change to how the m.call application in MatrixRTC works. And you kind of indirectly decline a call if you don't join a call. So there is a specific duration, how long it will ring, and like not answering to this duration is basically a decline. But yeah, I really like the question because this is something which would be super nice if there's even more metadata where if you send a ring, people can then maybe react to the ring as like, I don't want this ring. And then you could, of course, build beautiful UI around it, saying this person disconnected. And with the ring, sorry that I do another add-on information here. With the ringing, you could, since it's like such a separate system, it would be really easy to also say, I'm still missing person A, let's ring this person again. So that's also something that could work. And then if you decline, you could, like there's like so many things you can just build with normal matrix events. We just now went with as simple as possible. And we would go with the approach that then if there are new ideas and new improvements, we just built MSCs on top of this and basically have then a chain of MSCs improving the m.call application for MatrixRTC.
I wanted to ask, how many users can be in one call and what would be limiting factors?
Also a very good question. I basically steal all the information from Florian's talk about element call. So if you want to have, because there also was a discussion about it, you can watch the recording there. But basically the gist of it, it's 500 people with a mediocre AWS thing, so like 8 gigs of RAM, I think, for core machine. And yeah, of course, like there's not too much compute it needs to do, mostly the TLS decryption, and then it's just, you need a good network connection. So yeah, approximately 500 is a okay answer.
One more question. The delayed events, are they customizable from the client side or really?
Yeah, so basically you can send whatever delayed event you want, like any kind of event. You just need to put the delayed query parameter in there, and then it will be sent as a delayed event and can be interacted with refreshing and canceling and sending immediately.
Does it keep on the heartbeat still?
The heartbeat is basically just using the delayed, so basically the delayed event spec. Just say you can send a delayed event, and then you have this additional endpoint to refresh the timeout in this delayed event. So the heartbeat is basically just a trick or a specific way to use the delayed events.
But can you schedule a delayed event without the user interaction? Sorry, can you schedule a delayed event without the user interaction?
Oh, of course, yeah. I mean, a client can always do anything without user interaction. So if your client behaves in a weird way and just randomly sends events to a room, that works. Depends if people actually want this. So yeah, you could write a client that just randomly, without user interaction, or after a specific pattern, but without user interaction, send the delayed event. But of course, the client needs to be connected to the home server. The transition from the event being in the delayed state to go into the DAG, for this, you don't need the client to be connected. I hope that makes sense.
Thanks a lot, and we still have 5 minutes, so over there.
About the security and the encryption algorithm, when you need to recompute the keys, does it take a long time, like 1 second, 500 milliseconds, and do the user notice when it happens?
Okay, so for this, I think I'll go back to this slide real quick. So basically, recomputing the key isn't really a computation you need to make. You basically just generate a new secret, so that's like pretty low effort. The tricky bit then is exchanging this key with all the other participants. That very much depends how well your home server and to-device message distribution works. And sometimes you also need to do some more exchanging of to-device messages to first have the OM channel in the first place. And basically the way you would implement this is that you do an estimation how long it takes. Let's say like 7 seconds, 5 seconds. Then you exchange the key, wait for 5 seconds, and then you do an immediate switch on your S-frames, like on the pieces of streaming data. And in the best case scenario, the receiver already has the new key, and then it's basically a no-op. So there's no compute needed to exchange the key. Of course, a decryption step is still required, but for the receiver, it's basically completely unnoticeable. And there's also the discussion, do you really want to do this with a timeout, or do you have the network to basically communicate, hey, I already received the key, so now is a good time to switch it. That would be super nice. Even LiveKit could be used for this. So there's like lots of things you could do for optimization, but even just a timeout performs really well in real life. So just giving it 3 seconds, like sending the key, waiting 3 seconds, switching the S-frame, and then everybody usually has the key already.
Actually, an additional question. Sorry. Who is in charge of doing this? Is there some kind of SDK, or do we have to re-implement it?
So basically, the LiveKit SDK helps a lot with this. So the option that you have those insertable streams, that's the web term for this, that you can encrypt data which you stream through a WebRTC connection, that needs to be supported by the browser. And then you, of course, need an SDK which can like define which key to use to encrypting and decrypting it. And the LiveKit SDKs are super helpful there. So basically, they have a class, which is a key provider, and then you just put in the keys with the indices. So you basically fill in this database, and then they automatically go ahead, see, oh, there's a new S-frame. I have the key, I use the key, and it all works automatically.
Thank you very much, Timo. And give him a warm applause again.